illegal hunting or poaching, reckless deforestation, mortality rate becoming more than the birth rate, natural selection, or a catastrophe. These are some of the factors which can lead to something which we call extinction. Today we'll be discussing about some mathematical ideas behind extinction of a certain species. In this video we'll take this bird as a reference for understanding the ideas. Suppose you take a male and a female bird and breed them and account for the total number of birds in every generation. Let's define generation as 1 year. Say in the first generation, that is after 1 year, the population becomes 3. In the next generation it becomes 5. Then it becomes 9. Observe that the difference in population in every generation increases as the population increases. So it's clear that the rate of change of population is directly proportional to the present population. We can write it as a differential equation, replacing the proportional sign by multiplying a constant on the right hand side, which basically gives us an idea regarding how fast the population is growing or declining. We are concerned about declining population in this video. So we can now find a function which can tell us the population at every time step. But instead of taking the function directly, we modify a bit by introducing an upper bound to the population. As we know, owing to the limited availability of resources like food and various other factors, the population can't grow indefinitely. The following expression simply means that the population is allowed to grow till a certain limit and it becomes stable after that. So we have the following expression. Now we define T0 as a time when there are N0 number of birds. We are concerned about the time when the population is expected to get extinct. So we can take the time when there will be only a single bird left, as any further growth of population is impossible after that. But why did we take 1 bird instead of 0? Well, we'll come back to it later. Now by integrating both the sides and applying the respective limits, we get the following expression, which tells us the expected time when the birds will go extinct. Now note that if we had taken the limit as 0 instead of 1, we would have encountered natural log of 0, which can't be evaluated. In their foundational work on ecology and extinction, the theory of island biogeography, Robert MacArthur and E.O. Wilson proposed a simple model with discrete per capita birth rate and death rates. So it can be understood that per time step the total change in population is expected to be mu plus lambda. The total time for a population of size x to go extinct was given by the following expression. This term says the estimated time for the first change to occur, that is either a death or a birth. This term is the probability that the first change is a birth, and this term is the probability that the first change is death. TEX is the expected time when the population will go extinct. Although there exists a detailed proof of this, but the idea can also be understood intuitively. Consider there are X birds present. If the first change is birth, then clearly the new population is X plus 1. So the expected time when it will go extinct is clearly TE of X plus 1. Similarly, if the first change is a death, the new population would become X minus 1. Hence, the extinction time will become Te of x minus 1. Next, we simply multiply the times with their respective probabilities. If we consider a stable population, we will be basically interested in the total extinction time. In order to do that, we take two cases. First, if the growth rate is density dependent, in other words, the growth rate will become zero after the population hits a particular number. We get the following expression as a result, where Te of k is the following and Te of 1 is the following. In the second case, we assume that the death rate is density dependent. As a result, we get the following expression for Tek and Te1. Now, what actually is density dependence? Suppose there is a certain population of birds existing, but you observe that it does not grow beyond a certain limit, probably because of limited food or predations. The growth and the death rate can hence be dependent on the current population, which we call density dependence. Mathematical analysis like this play a significant role in figuring out the critically endangered species so that we can take necessary actions before it's too late.